Well, welcome to our third Friday Forum. I'm Keith Brandt. I'm the Vice Chancellor for University Relations. It's my pleasure to invite you here. I'm going to be doing a little ping pong here, it seems. We started out this series in January with a talk on immigration, and last month we focused on pediatric cancer. Today the topic is water. So we're trying to bring you some of our terrific faculty talking about issues that are important to the community, and that's our goal. Please spread the word. It's the fourth Friday of every month we're doing this. The topic today is water, and my goodness, what a difference a year makes in terms of the conversation. Obviously, for many years we've been talking about the drought, and this year we're talking about water damage a lot of the time. But we do know that we will, inevitably return to periods of scarcity, if not long-term scarcity. And so today we want to introduce you to a collaboration that's going on between a member of our faculty and an alumnus who are working together to address long-term water sustainability. Before you get to meet the speakers, I want to just give you a few facts about the campus water use because I feel we are often misunderstood. Water, although we are the biggest employer in Santa Cruz County and a large community unto ourselves, we only represent 6% of the water usage in the Santa Cruz Water District service area. So, in fact, of all the 10 University of California campuses, we are the lowest per capita use of water of any of them, and one of the lowest in the state at any large institution. So, we take our role in sustainability very seriously. And let me give you another illustration of this. In 1988, our student enrollment was a little over 9,000. 1988, little over 9,000. In 2015, 25 plus years later, enrollment was about 17,000, over 17,000. So in that 27-year period, we almost had a doubling of faculty and staff and students. Our water consumption in 1988 was 158 million gallons a year. Our water consumption in 2015 was 156 million gallons a year. So we have gotten incredibly efficient with how we use water on campus, which we're very proud of. In fact, the campus is an interesting place because unlike many major universities, we don't have a lot of big buildings. We have a lot of little buildings. In fact, there's over 500 individual structures on campus. And one of the things we've done is for most of those structures, we've added water meters that are electronically monitored hourly. So we actually have in quite advanced technology in monitoring water usage, and within a very short time can identify leakages and other issues that can be addressed quickly. So we've got I think we're very proud of our own water conservation on campus and what we've done. So I just thought since the topic is water, just share that with you and hope you'll join us in appreciating what we're trying to do on campus. So now let's get to our speakers. In fact, I want to introduce our speakers. I want to invite Paul Kochup. Paul's the Dean of Physical and Biological Sciences, who will introduce our speakers.
Yeah, as Keith said, I'm the Dean of Physical and Biological Sciences, and been at Santa Cruz for 20 years, a little more than 20 years now. I've been Dean for 6 of those years. And before I introduce the speakers, I want to say just a little bit about the sciences at Santa Cruz. The sciences are thread all through the community here on the Central Coast. You know about us physically. You've seen the Coastal Science Campus. When you go to San Jose, you can see the Lick Observatory on top of Mount Hamilton, and from Big Creek to Año Nuevo, we have a series of natural reserves where we study and preserve the natural beauty on the coast. There are, at this point, about 160 faculty in the sciences at Santa Cruz. There's 4,200 science undergrads, and there's over 500 master's and PhD students, graduate students, that are doing that work and not using water very wisely. And so we have a big personal impact on the community. And then finally, we have just a bottom line impact on the community. The sciences are about $100 million a year operation at Santa Cruz. $40 million a year is the core budget for teaching and research, of teaching and staff. And there's about 60 million a year that comes in through sponsored projects that our faculty go out and hustle money for and bring that to this community. All of that, by the way, well, a big chunk of that is endangered by the federal budget cuts, the 60 million part. And pretty much every day our scientists make amazing discoveries. I just went online and looked at the press releases for the last 2 weeks, and I'm just going to give you a couple highlights. So Beth Shapiro in evolutionary biology used ancient DNA from old-timey fossil bisons to figure out when bison got to North America. Noah Finnegan, who's in Andy's department and my department, figured out how rivers changed their beds in rapidly eroding landscapes, kind of changed our thinking about that. Carrie Parch, a chemist, figured out the mechanics of a biological clock that tells time, 3 molecules that interact to tell time inside of organisms. X. Prochaska in astronomy got a picture of early little baby galaxies forming, and there are these giant clouds of hydrogen around them. One more. Yeah, Terry Williams in ecology and evolutionary biology, who studies the physiology of marine mammals, realized that when whales in particular are doing deep dives, their physiology is in such a heightened state that loud noises or sudden strange noises freak them out and probably are causing strokes, and that may be the cause of strandings. She's pushing on that. So lots and lots and lots of basic science about, the universe, our place in it, how we work. But another great thing about Science at Santa Cruz is that it absolutely focuses on impact, on things that matter for society. The scientists at Santa Cruz are not afraid to get their boots wet. And there is no better example of that than our speaker today, Andy Fisher. I'm gonna introduce Andy and Daniel, but first Andy. Andy is a professor of Earth and Planetary Sciences. He's, before coming to Santa Cruz, I guess I would say he was best known for understanding how water flows through the ocean, through the floor of the ocean. So a core question about how the planet functions chemically and how it loses heat off the ocean floor. But for at least the 20 years, probably, Andy's been studying freshwater, but the water up on land and groundwater. And that's what he's going to focus on today. And he's done that with remarkable collaborations that cross between biology and chemistry and physics. Andy, as I said, is a professor of Earth and Planetary Sciences. He got to Santa Cruz 1 year before me in 1995. He received his BS in geology from Stanford, and then his PhD in marine geology and geophysics from the University of Miami. Before I let Andy up here, I'm gonna introduce Daniel as well. In his role as the Director of Resource Stewardship for Sustainable Conservation, he works closely with Andy on projects that have an impact for society. Before joining Sustainable Conservation, Daniel worked for 17 years for the Natural Resources Conservation Service, providing leadership and advice to counties around San Francisco Bay and the Delta region on water sustainability projects. And he also played a central role in a multi-county project to ensure the quality of the water that goes out to the Monterey Bay Sanctuary. And Daniel is a proud alumnus of UC Santa Cruz. He is a graduate of Rachel Carson College, formerly College 8, the college formerly known as College 8. And he graduated with a degree in environmental studies from UC Santa Cruz, and then he earned his PhD in human ecology from UC Davis. So let's welcome Andy. Okay.
Well, thanks, Paul, and thank you all for being here today. It's really nice to see the group. As Paul mentioned, Daniel and I, our paths have sort of meandered and crossed multiple times in the last couple of decades. And even when we're not directly working on a specific project together, we're sharing ideas and talking, and it's one of the ways that we try to get this work to be really translational, to try to bring some of the results that we find out into the fore. Today I'm going to talk about groundwater sustainability. And I'm really am focusing on collaboration. And in addition to Daniel, I see other collaborators out in the audience, so it's a great example. And some of them will come up here. You'll see in the title slide, my co-authors include Chris Coburn, sitting over there, the director of the RCD of the Resource Conservation District of Santa Cruz County. And there's other RCD staff here. There's also a big student group, and I get to present some of their work as well, which is always fun. So when we think about groundwater throughout the state, California really is facing three threats simultaneously. One, of course, is increasing demand. And I don't have time to go into that today, but we have a structural deficit in the state with regard to surface water and groundwater. And this is a pretty profound issue that needs to be addressed. But the other two issues are really more focused on climate change. And that's the shifts in land use that are taking place and changes in climate. The big change we're seeing in climate, which comes both from the model predictions, but also from the record from the last 120 years, is that we're getting more rainfall in a shorter amount of time. And you can see it. You can see it in wet years and you can see it in dry years. And that changes the amount of water that has time to percolate into the ground. So these are three separate issues, but they conjoin to create really a slow motion crisis in water supply and ultimately in water quality as well. Now, stormwater has been recognized for some time as a potential resource, although we tend to treat it like a nuisance. We tend to try to just shunt it off the landscape as quickly as we can. In urban areas, we often will do these low-impact development projects. They're located close to the source of runoff, vegetated swales, pervious pavement. And these are good things to do. They get water in the ground, but typically in modest quantities. At the other extreme are these big projects like the Orange County groundwater recharge system shown here. Large infrastructure, extensive engineering, water treatment, monitoring. They're affordable in wealthy, particularly urbanized areas. They get hundreds of thousands of acre feet potentially into the ground in a given year. We've been focusing really in between these two scales. We've been focusing at the scale of hill slopes and catchments, topographically defined regions that generate significant quantities of high quality water, which tends in this area to flow to the ocean while the rivers and streams are at flood. And if you think about that, it's really a tremendous loss opportunity when we can collect a tip off of those flood flows and hold some of that water back so that it's available for environmental purposes and for human use as well. These kinds of projects we target on the order of hundreds to maybe 1,000 acre feet per year. It's real water. It's significant amounts of water, but it's at a smaller scale than these regional spreading grounds. So I'm going to give you an example of one of these projects and tell you a little bit about how we're trying to make more of them happen. Here's a map of our region. Santa Cruz would be right off the map over here. There's the city of Watsonville. The purple area is the drainage basin for the Pajaro River, and the orange area is the Pajaro Valley groundwater basin. That's southern Santa Cruz County and northern Monterey County, a little bit of San Benito. And Santa Cruz, the city of Santa Cruz is unique in the Monterey Bay area. In an average year, we get most of our water from surface supplies. Everybody else is virtually 100% dependent on groundwater. The whole Central Coast hydrologic region from Santa Cruz down to Santa Barbara is 85% dependent on groundwater, more than any other part of the state, and the only one of the hydrologic regions in the state that is off the grid in terms of statewide and federal big water transfers. So we're on our own and have to learn to make do with the resources we have. And we're also ground zero for really high value ag, for caneberries and strawberries and table crops and organic vegetables. 30% of the farmed acreage in Pajaro Valley is organic. These are very, very important crops and industries and regions for us. If the Pajaro Valley were a county, it would be the smallest county in the state, and it would be number 5 in farm income. Okay, so this is no small thing that we try to figure out how these systems can be sustained in a productive way. And the Pajaro Valley Water Management Agency, which manages water within this area, it was created to deal with overdraft. It was created in the 1980s. And it's now become kind of an example that people are looking at for ways to manage water more effectively. This is the Pajaro Valley Water Service Area, shown with the outline. And within that area, the overdraft, that is the amount of groundwater that's pumped every year that's thought to be removing water from the available supply that's not being replaced, is around 12,000 acre feet. Around 20% of what they're pumping is overdraft. And there's seawater intrusion along the coast. The area in red here kind of marks where that intrusion occurs. There are no water imports, again, and they've recently adapted a management plan that includes conservation, water recycling, which they're already doing, and enhancing supply with managed recharge. Within this district, growers or municipalities or landowners who pump water from the ground, they pay what's called an augmentation fee for the privilege of pumping that water out of the ground with their own wells and pumps. It's about $200 an acre foot for most of the basin. If you're within this pink area, you pay more. The pink area is what's known as the delivered water zone, and that's where agency projects blend groundwater, recycled water, and then deliver it through a pipeline, through one of those purple pipes. And if you're in that zone and you pump groundwater, you pay a little more. If you get delivered water, you pay even more, right, for that water, because you're receiving that so-called project water. So what does one of these stormwater collection systems look like? Here's a site where we've been working with the landowner and a tenant and the RCD and other partners. It's an actively farmed ranch. The drainage area is shown here with this sort of tan area. It's about 170 acres. And water that runs off from this area is routed through a little settling basin where sediment can collect, and then into a 4-acre infiltration basin. And the idea is to collect water off of these hill slope areas before it reaches a blue line stream, before it becomes part of a stream channel. And then just hold it there for a little while to let it infiltrate into the ground. And of course, there would have been more infiltration in the past before we started manipulating the landscape. One of the things that we do when we build roads and we cover fields with plastic is we tend to generate runoff. So one way to think about this is it's a way to restore part of that function that existed before we came onto the scene. Here's a result from the last 5 years of the data collection we've been doing, and it doesn't include the current year. I was just talking with a colleague. Our instruments are out there right now, and we can't wait to get out and recover them and get the data. And neither can the landowner. And I'll tell you about that in a moment, why that is. But this is the last 4 years, and one of our students, Sarah Baganskis, who's a PhD student, this was her project, and this shows annual precipitation in centimeters, and then the amount of water that flowed into that infiltration basin. This is acre feet. Our goal was to get 100 acre feet per year. And Sarah, when she started out, she didn't know she was arriving at the front end of this drought. And so, we were a little concerned, but then something interesting happened. The last year of the drought, which was quite severe, we actually hit our target, over 100 acre feet in water year 2015. And you might remember that year, in December 14, that's the front end of the 15 water year, it rained for a week. And during that week, one afternoon was crazy. It rained, most of the rain in that storm happened in one afternoon, and that's mostly what this is one event. And it just crystallized this whole point that if we're not ready for the intensity of rainfall, then we're really going to be missing out, right? The last year, which was an El Nino year in terms of many indicators, was kind of a historical average year for us in terms of water, but again, we hit our target. And so, what this project is telling us is that it's possible in both dry years and normal, and I dare say wet years. I think we're going to be up here this year. That we can actually achieve targets in projects like these that are pretty low tech if we're careful about how we set them up and how we put them in. Well, here comes the higher tech part. We just wrapped up a project in collaboration with the RCD, with Sasha Lozano and others at the RCD, to map all of Santa Cruz County and northern Monterey County. Here's Pajaro Valley, groundwater basin. And this colorful map indicates where are the good places we might look to do recharge projects. And this is based on pulling different data sets in from the feds, the state, the county, local agencies to combine all this data and shuffle it together and stack it up and try to find the spots that are the best. And the ones we think are the best are in green, and the places that we think are not as desirable are in the pink color on this map. And I felt like I was living a dream about 3 weeks ago, sitting down at a meeting with Sierra Ryan, who's here with the county, and there we go, and others, to take this map and others and overlay parcels from the county and from other areas from Soquel Creek and say, okay, where can projects be put in? That was the goal all along, was to help facilitate that. But the other thing we're looking at is the water supply, and this result up here is one of our modeling results where we modeled how rainfall could run off the landscape. So this is where you might get it in the ground. This is where the supply is. And of course, you can now overlay those and try to find out. And it's interesting. You see this area with relatively high runoff right in the middle of the basin. Well, that's the city of Watsonville. That's an urban area, impervious cover. It's relatively flat. You generate runoff from that. Interesting up here in Corralitos also, that's where the Purisima Formation outcrops. You generate a lot of runoff there. So if you know sort of where to look, we can find these opportunities by overlaying different kinds of maps and figuring out where these projects might be done. These data sets are up online. We just handed off a bunch of the model results that are going to go online. And part of the goal is to share all this, push it out into the community, and let everybody work with the information. So we're excited about that. All right, as I wrap up, though, I want to finish with this next piece, and that's how can we help to create incentives so that more projects like these can be done. And the big issue is that they take land. So this is Pajaro Valley's managed recharge site at Harkins Slough. This occupies about 7 acres of land surrounded by working farms. But it also requires maintenance. And in this case, you can see the sediment that collects after each year, and it needs to be scraped out. You can see the piles of scraped sediment here. Here's where it hasn't yet been collected. So there are costs associated with these projects. How are we going to pay for them? How are we going to get landowners to engage with us and engage with agencies and others to make these projects happen? And there's a model for this. It's been very effective in California, and it's called net metering. It's been applied to solar panels and electrical power generation. So the way the program is set up here is that when power is generated and it's more than is needed, it can be put back on the grid. And back in the day before we actually had smart meters, when there were physical meters, they would do this. They would run backwards. They would literally, you could go out of your house and watch your meter run backwards. And this is just viscerally exciting, right? I mean, people really get excited about this. So our thinking was, well, how can we do this with groundwater? Because it hasn't been done before. And let me show you how it could work. So imagine we've got a ranch, 75 acres, and if we're going to grow these tasty berries, we need 2.5 feet of water per year for those crops. They are water-intensive crops. Okay. So imagine precip in the area is 18 inches a year of rain, and let's assume the runoff is 40% of that, a fraction of 0.4, which is pretty typical based on our field data when we have intense storms, when we have these big storms. So now imagine that the couple of different size drainage areas. These don't need to be the farm. They can be the surrounding areas. Water doesn't care about property lines. Water runs downhill, it runs across fields. So just imagine different size drainage areas and then hypothetical infiltration sites, different sizes. In this case, let's assume that the grower or landowner is paying this augmentation fee of about $200 an acre foot. And let's assume we can have a rebate so that for every acre foot in the ground, the landowner essentially gets a credit, 50% of the value of the water. So here's how that pencils out. For that rancher not participating, they're going to be pumping about 190 acre feet to support their berries. Okay. On the other hand, if they can drain from 200 acres and collect that water and put it in the ground, then in fact they're getting about 130 acre feet of infiltration, and therefore their net pumping here is about 61 acre feet. So they've driven that down by 2/3. And if you have a drainage area of 400 to 600 acres, then they're not just farming berries, they're farming water at the same time. Okay, there's a net inflow of water into the ground for these last two scenarios. So the net pumping is negative. And now tie in the rebate. For the non-participant, they're going to pay about $38,000 for water in a year. It's a lot of money. Berries are a valuable crop. It's worth paying that money for that water. But that same grower can earn all of that money on the berries. And if they're willing to put in 400 water draining from 400 to 600 acres, then their net augmentation fees can actually be driven to zero. This little pink curve shows the rebate, and it actually exceeds their water cost here at the end. Okay, so they can actually be growing their crop, preserving the agricultural values of the landscape, and making a little bit of money and putting more water in the ground than they're taking out. Okay? And this isn't just an idea now. In collaboration with the Resource Conservation District, we pitched this to Pajaro Valley Water, and after consideration by the board of directors, they approved the program. And it launched in October of this last year as a 5-year pilot. And the idea is to put 8 to 10 projects in the ground over the next 5 years, each one generating about 100 acre-feet a year or more. There'll be a third-party certifier to identify the sites, raise the capital costs, develop engineering plans, and then build the systems for measurement. And this is really important because in many cases with things like low-impact development, we can't actually measure the impact very easily. If we design the systems up front to measure them, then we can actually quantify the benefit. And that's very important for management. The third-party certifier would then work with landowners and tenants to make the measurements, collect samples, validate performance, make a report, and then those numbers would be used by the agency in order to calculate a rebate. And in fact, the plan right now is that Pajaro Valley is not just going to rebate a credit, they're actually planning to cut checks. So the participants are going to get a check in the mail, and it's going to be a big check, okay, for putting more water in the ground than they use in some cases. The current status is we have one site that's fully operational, the Boca Risa site that I showed you earlier. One that's nominally been approved for funding from a grant that was written last year. It's in the permit stage right now. There's others in development, and there are a lot of phone calls and emails coming in for people that are interested. We don't have to worry about that. I think the issue is capacity, how many projects can be handled. And in case you're wondering, for this recharge net metering program, the RCD of Santa Cruz County and UC Santa Cruz are partnering as the third-party certifier. So the goal is that we're going to help to pick the sites, raise the money, make the measurements, show the benefit, and do the experiments that we need to do to show how the systems work, and incidentally, how we can improve water quality at the same time. All issues that are of concern. Okay, so one way to think about this is that the net metering program is this three-legged stool, and there's 3 sources of effort and revenue that are required to make the project work. The rebate is actually the smallest of the smallest of the legs, I guess, or the smallest amount of money that's actually needed. The others are the capital costs, and these are for things like identifying the sites, designing the systems, the engineering, the infrastructure, actually putting them in. And then the other big cost is in the measurement, the sampling, and this certification. Each site is going to have to be analyzed very carefully with data collection, sample collection, and then a report generated each year, which becomes the official record of the site performance. And the agency and the landowners, the tenants, they agree up front to accept our numbers. So, in a way, it doesn't matter if we're wrong. If we're close, it's good enough. Right? Because really the point is to just keep putting the projects on and keep getting that water in the ground. We do the best quality work we can do, we get the best numbers we can do, and we're just not going to argue about the numbers. And everyone agrees up front that that's okay. And as the one of the members of the board of directors said for Pajaro Valley Water, this is inexpensive water. It's highly competitive from their perspective compared to the alternatives. Okay, so financially, we think this can be sustainable, but that's one of the things we're trying to figure out. I just want to wrap up then by noting that the net metering approach is novel in several ways. You've probably heard about groundwater banking, and the concept of an aquifer as a bank is problematic. The nice thing about the net metering program is that we're not incentivizing ownership of groundwater. It's incentivizing a behavior, which is putting the water in the ground. And then we claim the win at that moment. And by doing that, we're able to step around a number of thorny issues like water rights, like ownership, like whose molecules are they? And if the water goes in here, who gets it when it comes back out? Also, the rebate is performance-based. So that creates an incentive to keep the projects going. And if they're not working, then they can go away and a new project can be brought online. And then the incentive is based on the rebate of fees. So it provides a value to water that's tied in a way that landowners and tenants can see right away. They can see what the effect is right away and see the benefit. I think there's probably a lot of creative ways we can incentivize programs, not just this one, but other programs. And I hope that we'll be thinking about some of those in California going forward. So to wrap up then, stormwater really is quite valuable, particularly for holding some water back so we can have it in the future. It's very useful for recharge, but we need to find the right places. And I think that's important, so we put our effort, our limited resources, where they can do the most good. We can improve water quality. I didn't have time to talk about it, but I'm happy to tell you more about testing that we're doing to show that. And the recharge is the benefit. It's not just the storage. It's the act of the water moving through the soil. That's the win. And when we recognize that, it creates opportunities then to create incentive programs. None of this could work without collaboration. That three-legged stool is probably like a nine-legged stool of collaboration, ultimately. It's the RCD, and it's us, and it's the agency, and it's the stakeholders, and it's the NGOs. It's everybody. And if any one of those pieces were not willing to work together, then it wouldn't work. And in a way, it's the dependence, the interdependence of these groups that makes the projects function, I think. So with that, I just want to acknowledge funding from a variety of sources that supported these projects. And I think I'm just going to hand off to Daniel, and maybe we'll answer questions together when this is all over. So thank you very much.
Great. Well, great introduction for me, Andy. Thank you for that. I wish I had faculty like Andy when I was here back in 1980s. When I was here at that time, what we were challenged by our very disciplinary academic instructors was take all these ideas and bring them together, because there really wasn't as much of sort of the integrative type of thinking that Andy displayed here, from the geology to the economics to the social acceptance issues. And in environmental studies, we were really being taught by these disciplinary experts and asked to bring it together. So my subsequent many years I've been really trying to put that into practice as we were challenged at the time. I'm going to take us to a bigger scale in the state. As Andy said, our lives have we keep orbiting each other and sharing ideas. This whole idea of groundwater recharge is something that we've also been working on at Sustainable Conservation, which is a nonprofit, California-based nonprofit, focused on finding resource solutions that make economic sense, primarily with the agricultural community. And this is an artist's rendering of what the state looked like before we started to manage the interior part of the state. And what you see in this picture is very large water bodies, wetlands through the entire Central Valley, the snowpack melting down into the valley. And one of the things that I learned through sort of the agroecological perspective here at UC Santa Cruz is how can we manage our resources in ways that build on natural processes rather than fighting them. And then from an economic perspective, that's a major opportunity for cost savings. So as humans moved into, or the Europeans moved into California, this whole flooded Central Valley was drastically altered. We started to drain those wetlands for agricultural purposes, for urban purposes, and we started to recognize the need to protect them from flooding. We built bigger levees. And essentially what we did was we separated our floodplains from that natural recharge process of water coming down out of the mountains during the winter and through the snowmelt in the Central Valley case. By eliminating that water supply, funneling it down these rivers, we created a much greater dependence on groundwater, and were able to use surface water when it was available through canals, diversions off those rivers. So the Central Valley has a very different system than on the coast, where it has both groundwater and surface water reliance. But with the climate change conditions that Andy talked about, the ability to tap that surface water has become increasingly rare. The last 5 years, there was virtually no water supply off these diversions. And groundwater pumping has increased, not just in the drought years. This graph takes us back to the 1920s. And really, with the advent of deep pumping capacity, farmers in the valley realized that they could pump water from deeper and deeper levels for cheaper and cheaper costs with diesel and electricity, and groundwater has continued to decline for decades now. You see slight recoveries in this groundwater downward trend during wet years when there was enough water to put back on. Most of that recharge occurred either through the bottoms of the river channels or through farmers irrigating. And farmers irrigating with flood irrigation has a bad connotation. People think that's wasteful use of water. Well, actually, it was one of the few ways that we were able to offset that decline in the Central Valley's groundwater supply. The general population felt that all that wasted water on farmland needed to be controlled. Farmers started to recognize the economic value of higher value crops by going to micro irrigation systems, and we worsened our groundwater recharge problem. We eliminated one of the major sources of recharge on the landscape. So in our efforts to conserve water and save water during dry years, we eliminated our main source of recharge. And the other consequence of that has been subsidence, the collapse of these groundwater basins as the water was taken out of them and the clay particles settled. Now our major infrastructure, like the delivery of water to the Central Valley through the California Aqueduct and the major source of water to Southern California, is now threatened. Some of the flood capacity in the valley this year is being rated at less than 80% of its capacity as designed because these systems have settled so much they can't move as much water through them. There's low points where the canals have actually settled and we can't deliver water at the rates we used to be able to. Major economic impacts to the state, not just in the valley, but for Southern California and for the urban populations all the way up through the Delta as these flood conditions are going to get worse this year as the snow melts. So we've got some serious problems. This was last week looking at the San Joaquin River outside of its banks for the first time in a really long time in a reserve area. This is what the valley used to look like during flood events. We don't want this in our cities, and we don't want this on our farmlands. So the approach, taking sort of an agroecological approach, how can we bring that water back, is the idea of returning rivers to their floodplains in a managed way, using the existing infrastructure that farmers have used for decades to carry water off the rivers for irrigation during the summer. Let's use those same canals, take that water out onto that farmland, and put more water on the cropland than it would normally take when we have these peak years. These are fields that are intentionally being flooded this year to take that water, recharge it back into the groundwater voluntarily by these farmers who recognize that they're going to be facing restrictions on their groundwater pumping under the new California Groundwater Sustainability Management Act, and that they won't even be able to grow these crops there much longer if they don't play a part in solving the problem. We're working with those farmers to help them determine what is the right amount of water, what's the right time to be putting that water on, and measuring it, as Andy talked about, so that we can actually start to talk about what sort of credit do they deserve for those that are doing it. We're working with UC Davis that has developed this map already about site suitability. This is very similar to Andy's map, but just the top 6 feet of what soils can take water through them without causing waterlogging of the crop's roots. And then we worked with the Almond Board of California and another private company to look at the underlying geology and identify, if you get it through the soil, where is there space, where are the places where it's most overdrafted and where there's not geological barriers, really what Andy's map showed as well, but for the entire Central Valley. And it turns out the areas in green on here are the areas with the most severe overdraft to start with. So we're very fortunate that the sandy soils overlie the places where most water has been taken. So we're focused in the San Joaquin Valley and the Tulare Basin in the south, mostly. And working with UC Davis is doing crop evaluations to figure out if you take these tubes into the ground, what happens to the roots when you start putting this kind of water on to permanent crops like almonds and grapes and pistachios, which are the main crops in the valley. And are we going to threaten those crops' productivity in the short term with disease and the long term in terms of their productivity, which has really gone up with the advent of drip irrigation. They've actually raised yields by using less water, has created this major economic engine for these crops to be sustained in the valley. And contrary to sort of public views, almonds have reduced their water use by over 1/3 in the last 15 years through this kind of technology. They're not as big a water user as oftentimes characterized. But we want to know if these almond farmers can actually play a part in contributing to the groundwater recharge at the same time. A lot of this comes down to farmer acceptance and farmer recognition of both the value, but also what do they get back from it? Because not every farmer sits on one of those green rated soils. So the farmers that do the recharge, that water out of that leaky bucket moves down to somebody else's farmland. They pump it back out. What do these guys get from it? So their top questions are, what's it going to do to my crop? How can I be compensated? How do I know how much water I've put in so that I can get some credit for it? All scientific questions and economic questions that have to be answered for them to participate. We started with one or two farmers. In fact, the barn of this farmer was the first farmer that did this back in 2011. His neighbors in that year said he was absolutely mad and crazy and didn't hardly want to associate with him. Now we can start to fill the barn up with a few more neighbors, and that was 2 years ago. This year, I think his barn would be packed with folks wanting to know what can be done. And with the groundwater legislation and the possibility for assessment on all farmers for their groundwater, this is a possible way, as Andy discussed, to reward those that are participating. The other really interesting collaboration that's formed out of this is the food and beverage industry. They are severely concerned about the reliability of food supply from California right now. They see this trend in groundwater. They see the new regulations. They've got major processing facilities in California that they've invested in, and if their supply chain is cut by 20 or 30% due to lack of water, that's going to completely change the bottom line on those investments. So these companies are now investing in this research, helping to pay for the kind of projects that I described a minute ago to help determine if this can be done and how quickly we can get this concept working. So our primary strategies right now to move groundwater recharge to scale is really addressing these two major groups: the farmers' acceptance through both the agronomic and economic pieces, and groundwater sustainability agencies, which are they're the water agencies of Santa Cruz County, but across the state, that have to make the decisions about how are they going to manage these supplies in a sustainable way. And with them, they need to figure out what proportion of their water supply can they actually offset using recharge. Can they do this in a feasible way, or do they need to start taking land out of production, building more catchment basins, larger permanent basins like we saw down in Orange County images? I want to switch back to the Central Coast here for a moment, and a project that we're working on with the Resource Conservation District and Driscoll's, and really looking at the other side of this is the water conservation side on the coast. We don't have giant snowpacks here that we can rely on. We don't have as good as soils for recharging the groundwater. The numbers that Andy was talking about of 12,000 acre-foot deficit in the Pajaro Valley, 5,000 acre-feet of that need to come from conservation. The other pieces are recycling and recharge. So conservation is a really big piece in this region to get us there. And so we've been looking at how do we move farmers from their current management to see if there's what level of efficiency can they achieve that they haven't yet achieved. And both in terms of water management, but also in nutrient management, which is related here in this valley. And the key piece on this is farmers that monitor actually improve management. But getting them to monitor in the first place is the big hurdle. And this is a behavioral change challenge. And when the RCD has gone out and worked with farmers to see what kind of record keeping they have, is quite disparate. There's little pieces of paper in the back of the pickup truck, all the way down to information on the iPad and iPhone. Not every farmer is the same. There's a lot of variation there. How do we get these guys who barely keep track of it to be able to say what is actually going on? So the pilot project that has been going on now for 3 or 4 years in partnership with Sustainable Conservation in the district works with a number of different farmers and is actually helping them measure this efficiency. And we've seen some really amazing results in these last couple of years. At the beginning, the UC average data was farmers were using 33 inches per acre. That was about 144% of efficiency. In other words, they were using 44% more water than the crop needed. In the last 2 or 3 years, as a result of the farmers keeping track of the data, they've moved down to just 103% of efficiency. Significant reductions in water use just by measuring. Now by measuring, they then started to ask for technical assistance about how can I get my number lower? And they see their numbers compared to their peers and they go, why is mine at 144 and this guy's farming at 103? His berries look good. How is he doing that? So we've seen in that first round of using the metrics, a 24% improvement in efficiency. Next year it wasn't as much because they've already achieved a lot, but net 29% improvement in water use, 30% efficiency. If we spread that across all the farms in the valley, we can hit that 5,000 acre water conservation target. So we've started working now with lettuce growers in the last couple of years. And then finally, how do you get people to use the incentives? And this is really use the measurement techniques. And this is really the challenge. And part of this comes from retailers asking for it because customers care and want to know. That's actually driving a lot. And investors in those companies are asking these questions. Regulatory compliance is another option. If it makes it simpler for them to report to regulators about how much water they're using. The district, the RCD is looking at discounted interest rates right now on their loans, being able to offer them a discount if they can achieve those targets. And then this whole idea of just simply performance measures and peer comparison seems to be a really big driver. So those are all approaches that we're looking at right now. All these ideas bring together the science of the hydrology, the measurement, and the economics. So I will stop there.
We have about 10 minutes remaining for questions.
So, particularly when I think of this area, how, if you're catching fresh water, how do you deal with the whole fertilizer issue and the salt intrusion?
Sure. So, irrigation inevitably drives salt and nutrients into aquifers. It's unavoidable because you can't have 100% efficiency with irrigation. Then you'd have exactly as much water as you need, and you'd be building up salt over time. So the question really deals with what happens when we drive a little bit of salt. Even if you're really close, you're still going to be slowly adding salt and nutrients and potentially other compounds in aquifers. And this is a challenge. And there's kind of two answers. One is that when we look at runoff, the runoff coming out of the State Water Project, the Central Valley Project, or hill slope runoff, it's often pretty good in quality compared to the water that's already in the ground. So simply adding that water in general, sometimes we avoid the first flush, that first flow of water that comes off the landscape in the new water year. That's not the best, but we can let that go. We don't need to collect that. So by the kind of monitoring that Daniel showed, and we're doing similar things, we can see what that quality is, and we can make sure that we're adding water that's certainly better than what's in the ground, and in many cases, very good quality water. So that's one issue. The other issue is these trade-offs. They're not just trying to do this everywhere. They're looking at what crops are being grown, what are their fertilizer practices, what are their pesticide practices. So it's sort of aligning the recharge goals with the right places. That's part of it. For us, we look at targeting these relatively small areas. 2, 3, 4 acres is not much acreage. And so from our perspective, if you can find just the right spot, there are trade-offs. If you're flooding a field that's used year after year, potentially you're adding additional fertilizers year after year. If you pick one site and dedicate it, you avoid that problem. These are all trade-offs, and no one approach is the right approach for everyone. And also floodplain reclamation, bringing the river back to the floodplain. In many cases, this is a really good thing to do. Now, those soils might not be the best for infiltration, but if you flood a large area and you give it time, you get some benefit.
We've got a project that's going to be done in June looking at legacy nutrients in the soil down as deep as we can core, about 40 feet, and looking at the idea of dilution, what Andy was saying, and actually creating a program then that says, if you're going to do recharge, let's keep doing it on the same acreage over and over, because once you've flushed the last 100 years of legacy nutrients down, let's keep doing it in that spot rather than moving it around and flushing all this other material.
And I'll just make one more related point. I think this is important, and it's not always appreciated. When our aquifers were in their pre-development state, when the valley was the way it was, when the Pajaro Valley was the way it was, and the aquifers were full, every molecule of recharge that went in was matched by another molecule flowing out. Right. That's what a full aquifer looks like. In a full aquifer, you get none of the recharge back. You lose it all. That's what perfection is. But it's serving a purpose because it's flushing out the system. So as we raise water levels and we reconnect to the surface, in the long term, and it's going to take a little while, but that's how we ultimately prevent the aquifers from becoming terminal sinks for salt and nutrients. And this is, in a way, the biggest challenge we have. In other words, by not recharging, we are guaranteeing a problem. The biggest risk to water quality in groundwater is not recharging.
Let's go here.
Have you done any thought to smaller residential, say 5-acre, 10-acre parcels there's hundreds of wells in Santa Cruz County on 5-acre parcels. Is there any thought about those properties recharging?
We have, in our case, it was kind of a bandwidth issue for us. We're just a small program, and this is a pilot, and we wanted to really focus on places where we could show an improvement at a scale that is a fraction of the need, a significant fraction of the need. We would certainly encourage all scales, from the smaller scales to the larger scales. But from our perspective of funding and permitting and monitoring and reporting, whether it's a 10-acre site or a 200-acre site, it takes us about the same time. And so for the purposes of the pilot, we've kind of picked this middle ground. But I would certainly encourage that we approach all scales. I think Daniel would probably agree.
So with the introduction of a new, presumably high water use crop, does your modeling consider the marijuana crops that are going to be growing in the county?
Daniel, why don't you go ahead and take that one?
Actually, I don't even know what the water demand on marijuana. If it's, I don't think it's higher than some of the crops that we're already seeing. Actually, is my guess. I mean, it's a crop that has natural oils that prevent it from losing water. So it's, I think, at least in the Central Valley, alfalfa and cotton, probably use a lot more water than that. So, the economics is another key piece here. What we see as water becomes scarce is the shift to higher value crops. So, in some ways, a farmer can make the same income off of less acreage and less water. So any high value crop tends to provide greater, resilience in the face of shrinking water supplies.
One of the big concerns I have heard about are dealing with water quality, with pesticides and fertilizer use. Now, perhaps as the industry opens up, that will be easier to control or to limit. But yeah, it's going to be a concern in specific areas, certainly. Yeah, no, it's a good point.
There's been a lot of talk about using Loch Lomond to capture an extra couple of billion gallons a year from the San Lorenzo River, and perhaps using that in the triangle west of Scotts Valley, Santa Margarita Aquifer Basin sandwich, and that would be about 3 CFS to match what Scotts Valley is taking out. What do you think about those prospects? Is that doable with the geology you've seen?
Yeah, so we've delivered some of our map products that include the Santa Margarita groundwater basin, Scotts Valley, San Lorenzo Valley, and there are certainly sites that are amenable. The agencies there developed a groundwater model a couple of years ago, and what it shows is you can improve groundwater conditions with managed recharge. Some of that water is going to go to streams. And as you bring the water levels up, the more goes to the streams. Again, it's kind of like I described. So that's an issue because in many cases the issue is how much can you deliver, how much water can you serve your customers. And in an urban area, that's really one of the big issues. So I think the technical issues are solvable. I think there are places certainly. The big issues are going to be the economics of it, the regulatory part, the water rights. Historically, water taken from a surface channel and then placed on the ground to recharge was not considered reasonable and beneficial use. That's shifting, but we're not quite there yet. I think we're going to see from the regional board and from DWR some shifts in what's going to be necessary to achieve SGMA goals, the Sustainable Groundwater goals. So I think, technically, it's a great idea, absolutely, and it's feasible from that perspective, but there's a number of other pieces that have to be sorted out. And I guess the final thing with any reservoir system, it's the same thing people are struggling with all over California, is the reservoirs serve dual purposes. They're supply, but they're flood control in many cases. And that's, boy, do not envy the people who manage the reservoirs because they are in a no-win situation in many cases. They just don't know if this is the last storm or not and how much they should hold back.
And actually, we're looking at that in the Central Valley. After seeing Oroville and the situation there, the recognition of reservoirs and what their role is in the state in terms of flood control, but also water supply, there's the Corps of Engineers that manages the flood aspect of that, keeps the water, or requires a certain release in anticipation of snowmelt or other storms, as Andy was saying. But that water the water users want to hold as much back as possible because they want to have it for the summer. Releasing that water, if you knew you could put it into the ground, creates this entire new flexibility that we're looking at in the Central Valley, where you could release that water out even if you don't know there's a storm because you're just storing it in a different place. The water users can take that water, put it in the ground, pump it back out later. If they don't get a storm, they still have the water. If they get a storm, then they get more water stored. So we actually expand our capacity for storage in the state by expanding the flexibility of the system.
And I would agree with one nuance, which is that you get some of it back.
Some of it, correct.
And that's
that leaky bucket.
Yeah, and that's the thing that it's really important. People shouldn't consider 80 or 70 or 60% recovery to be a fail. It's important we frame these projects correctly based on how they'll work, and we know aquifers are connected, especially when we bring the water back up, the water levels back up. So I agree completely. I think as long as we're willing to recognize those issues, then it's a win-win when we can use the groundwater conjunctively with the surface.
So we're out of time. We want to keep on our schedule and want to thank